we said how to insert using overflow pages if it is not there a space in the primary leaf pages. Then you can delete, how you can delete the entries for data records from the files, and if it is in overflow pages the memory can be released and buffer space manager, disk space manager can take action to release the memory. So we had completed the ISM yesterday's class, and I had started also with the B+trees, right? And in B+trees we introduced in the unit 1 also how the data is organized in B+trees, right? Leaf nodes, non-leaf nodes, the height of the tree, then we said the fan out of the tree, right? Then yesterday again I have introduced a very important concept of B+trees, and that is the, if you remember, it is the order of a tree, order of a B+tree. So we say the order of the tree is D, right? This is the order, then each node can have the entries between D and 2D. So if I am saying the order is 2, right, then each node can have entries from 2 to 4. So M is my number of entries, right? And it is always, ensured that these many entries are always there in each node. That's why we say there is a 50% occupancy in the B+trees, right? So at any time in the node, in any node of a B+tree, there are always the M entries, and those M entries are between D to 2D. So if my order is 2, that means I should have 2 to 4 entries always in my B+tree, because this is very important. This we will maintain it when we do insert, delete and delete operations, right? So yesterday we saw the search algorithm also. In detail I have shown you the search algorithm with all the key pointers. Which were those key pointers, if you remember? The P0, my search key value was K1, then I am having pointer P1, my search key value is K2, my pointer is P2, then I am having K3, P3, and then lastly I had Km and then Pm. Right? This is the last search key value, if at all it is these entries in a particular node. Right? All the my entries, a node format we say in the B+trees. So we saw how a search algorithm we carry out. So if it is below, less than K1, we say that search this side. If it is greater than Km, then search at that side in the tree node. And then if it is not both, then find the value of K1 where it fits it, the search key value which we are searching for K. K is less than Ki and Ki plus 1. Right? Search such value and then you follow the node pointer. When following the node pointer, if you get another, index node, then you need to again continue the same process. If it is a leaf node, meaning is you have got the index entry, right? So all this we have done yesterday in the search algorithm. So let me start with the insert algorithm today, right? So when we are inserting in a B+tree, so again I am putting an example because we will be dealing with the values, because we know how the records are stored into the B+tree, and based on that which record I am deleting and how it takes the action, the ADBMS takes the action, how it organizes insertion and deletion in the B+tree. So let us find out. I hope it is clear, right? So we have a B+tree with 13, 17, 24 and 30, right? The example I have taken from book, same, which is there in the Ramakrishnan book, right? So we are having the 4 index entries. This is my non-leaf pages. To revise it again, these are my leaf pages where my records are there. My alternative 1 is used. That means 2 star is indicating employee record with employee number, the USN or employee ID 2. This is the employee ID 3, employee ID 5, employee ID record with employee ID 7, and so on. So your leaf pages are indicating the data records and your non-leaf pages are indicating the index records, right? That is index entries. So we are having a index file and then we are having down the data records, right? So now let us find out when I am searching. Yesterday already I have said for 5, then I will see it is less than this, so I will get pointed to this, and as it is a leaf node, my search stops. I will read the leaf node, it is there, so it will be retrieved. Now a leaf node 15, if I am searching, right? So 13, it is greater than 13, less than 17, I should follow this node pointer. That is what we discussed yesterday in the algorithm. So when I follow this pointer, I find out in this page, is there any entry, right, with the record with the 15? It is not there, so the result is no record found, right? So we saw the search algorithm very in detail, right, with the algorithmic steps. So now we are starting with the insertion algorithm. So let me continue with the insertion. Before we go for insertion, there are few factors which we will discuss. So that is, what is the height of the tree and how many entries I can have, how many records I can store, right? So usually what we say, a level 1 is my one page, that is my level 1 is root, no? So that root can take at the most 8 KB, right? Level 2 I can have 133 pages if I consider a height of 4. Now actually what we are considering, the typical order I am considering is, to explain it, if my order of the tree is 100, that means I may have, the node can contain the 100 entries. Order is what? My node can contain from minimum 100 entries and maximum greater than 100 and then less than 200, right? So I can have entries between the 100 to 200, right? So that indicates the number of the entries, right? So I am considering D as order of 100 and average fan out is 133. Now when I am saying my order is 100, let me put it again. When my order of the B plus tree is 100, indicates each node in the B plus tree can have entries from 100 to 200, right? So not 100 and I will say 100 to 200. So minimum entries there will be 100 in each node and it can have maximum of 2D. That is what we discussed here. How many entries? M. M indicates number of entries. And how many entries you can have? From D to 2D. So what is my D now? I am assuming if my order of the node is 100, then I can have in each node the entries of 100 to 200 index entries. The average fan out is what? The total number of the pointers in all the nodes, right? So fan out is nothing but how many entries I am having, based on that I will have a pointer, right? Because my each node consists of what? I am having a pointer, right? Then I am having a value, again a pointer, again a value and again a pointer. If I am showing 2 index entries. So this is a pointer, this is a pointer and this is a pointer. So average fan out is what I am taking, the number of the pointers in the total B plus tree, because that will differ. In one node it may have, you know, some 88 entries, or in one node it may have 100. I cannot say 88 because order is 100. So it should be more than 100, right? So in one node there are 100, in some other node it may be 102 based on data, right? So that will indicate me if average fan out I take 133. What is fan out we said? The pointers which are there, average pointers in my total B plus tree, then I can have with the height 3. How many records? Just check it. It is in the millions, right? So if I take this much, it is 3,52,637. If I consider this, actually it is 23,52,637 records I can have with the height 3, right? With the height 4, I even go more, 312 lakh. That means the 300 million I get it there. So that is how I can, you know, my database can be very huge, but still my B trees of height 3 can cover the 23 lakh entries, right? So that's why we say B plus tree is the most widely used index data structure by the ADBMS, right? Which helps you to access the data fast, fine? Maximum 3 IOs will be required to get any record out of my 23 lakh records, right? Okay. So now here we are saying how much the size is used, you know, the space is required. So at the root I need a one page, that will be 8 KB. At the level 2 I will have a 133 pages because I am saying my fan out is 133. So I require 1 MB. So total size is hardly a 133 MB. So for the size we did not bother. But only the point to be noted is with order of 100, right? Entries in a node 100, because for example, when I'm demonstrating with the 4 entries, right? But in actually there can be a 100 entries, and with 100 entries and total fan out of 133. Fan out is the number of the pointers of a node, right? Of the all the nodes in the B plus tree, and order is how many entries I can have, right? So the pointers can be 133, average we have considered, because when I am saying 100 to 200 entries, I may have total pointers the 201 if maximum 200 entries are there, but average I have taken it as a 133, that is fan out each node. So each node maximum has 100 entries, 100 to 200 entries, and each node an average if there are 133 pointers, that means the average there are 133 entries in each node, then we can have 23 lakh records can be stored, can be accessed fast using this indexing structure. So let us move to the next point. So what we discuss next is naturally how do we insert, right? So this is an insert algorithm in the B plus tree, right? I am putting this theoretically, right, from the book only, but you in book you have both the versions available, theoretical as well as using the search algorithm, how I said K0, P0, root load, right? So let me first put it theoretically how we find. When I am inserting, what I will do, when my B tree is there, I need to find the correct leaf, because I am inserting an entry, no, in the B plus tree. So I am having an index node up and then down I am having the records. So I will find a correct entry, correct leaf node for that. If there is if there is a space, enough space, then you just enter that entry into the leaf page. Just enter that record into the leaf page and it's done. You need not add, change, you need not adjust any index entries or any changes in the leaf nodes. So there is no absolutely change in the leaf node as well as non-leaf nodes if already there is enough space to hold that record. So first point is what? Find out the correct leaf where that entry should go, because in ISM as well as in B plus tree, the records are sorted, maintained in the sorted order, right? So find the proper space and proper leaf, and if there is enough space, it's done. Else what should happen if there is no space in that record? Then we should split the leaf node, right? We'll see the example. We split the leaf node and we redistribute the entries evenly. Why? Because we are saying the order of a tree is m entries I should have. So you cannot have if order of a tree is 2, because we illustrate an example with order 2. So if order of the tree is 2, then I cannot have it at any time in a node only one entry, right? So if it is happening after insertion or deletion, I should do the redistribution with the sibling node. So what do you mean by sibling node? A node which is next to it is your sibling node. So we will demonstrate this with example, right? So the point is what now? If there is a space, I found the correct leaf node. If there is a space, just make an entry and it's done. But it may happen that there is no space in the leaf node. So you need to now insert a node, new node. How do you insert a new node? You split the node where that entry has to be there, right? Because it may happen like you are having a record with 2, 3, 7, 8 and now you are inserting a record with 5, right? So you need to split that leaf node into the L and another one node. So I call it as a new node L2, right? And then you redistribute the entries evenly, right? So you need to do the adjustment for the entries because you had the 2, 3, 7, 8. Now you are inserting a 5. So you will insert a 5 in the first node and in new node you will have a 7 and 8. So we will find out that. Now if required, then insert an index entry pointing to a L2 into the parent. Why? Because you inserted into 2 nodes. No? So the entry in the index node also has to be made for the L2 into the parent node. Right? I will come back again for this theoretically after example. But let me finish once the theoretically how this insertion takes place. Now what happens sometime, there is again next level. Sometime it may happen that there is no space in the index node, right? So index node is also full. That time the index node also has to be split up, right? So to split up the index node, we should redistribute the entries evenly. So the same logic follows. what redistribution you are doing at the leaf nodes for the data records also happens at the index entries records, right? So redistribute the nodes at the index node and push the middle key. Why? Because you have added the entry for the L2 and now you want to add an entry for the L2 and there is no space. So you need to again split index node and then you push up the entry. So this will make a grow the tree. The splits grows the tree. The root split increases the height. Suppose if you are splitting at the intermediate level, so you have a root, right? Suppose you have a root and then you are having down the index nodes. So if your split is happening here, then height of the tree will not increase. But if your slice, the split is happening in such a way that it cannot accommodate here, you need one more at the another level. Then if you are putting a root there, new root, then height of the tree also grows, right? So there is a possibility of what? I get a space easily wherever it has to be placed the record, then just place it at correct leaf, it's done. But what are other possibilities? There may not be a space in the leaf node, right? So you need to split the proper leaf node where it has to be entered and then you split that leaf node L into L and L2 and then make an entry for L2. Fine, L2 is my new split up which I have done. Fine. Now it may happen that index node also has to be split up because index entries were full in the up level, right? So you are coming up level, right? So in up level index entries were full. So again you need to do the, either you need to make an entry if it was free, you can just make an entry and stop. But if it was a full, then you need to increase the height of the B+ tree. So you may need to change the root because there was one root with 4 entries. Now we cannot accommodate 5th entry. So we need to make a one more root. So I will illustrate this with an example. So once again, after this example, with example later you will get it very easily, right? So we'll come back again. So let us find out how we do that in example. Now what was happened in our old tree? Before I go with this diagram, what I'm trying to insert now, I'm inserting a record with 8. Right? So I am inserting a record with 8. So let me put it properly so that it's clear to you. Right? So my tree, which is I'm considering old tree, which is first example for search. So I am inserting a 8 star. 8 star is what? A record with the search key value 8. I am inserting into a B+ tree. Right? Now what was my position of B+ tree? Let us find out first the B+ tree. Correct? So now see here, first observe it carefully. So how was it? I had 13, 17, 24. Let me put it here. So what are the index node entries? My index node entries are 13, then I am having 17. Then I am having 24 and then I am having 30, right? What are the below less than 13 are how many? I am having 4 entries. Some which record? A record with 2, record with 3. It is just 2 level. One, this is index entries. This is one non-leaf level and one leaf level. So at the present I am having only that much was sufficient when it was created, right? Now second one I go with 14 here, right? So I am having the 14 star, then I am having 16 star. Now there is a space here, right? So there is a space for 2 records. After this I am having 19 star, then I am having 20 star, then I am having 22 star. There is a space for 1 record, right? So let us consider only this. So greater than 17 is going here. Now greater than 24 is going here, right? So let me consider only this part because I am inserting 8 now. Now when I am inserting, I want to insert a record with 8. What will happen? I need to first find out a proper leaf position, right? Where should be it inserted? So I will compare 8 with first value. As 8 is less than 13, this pointer will point me to come to this leaf node, right? So I need to do an entry here. Meaning is, right? But when I observe that, suppose there was a space, this 7 record was not there. I could have easily entered 8 record there and then it's done. I need not do any other adjustment. That is first step. But now what is happening? Second alternative. Now a leaf page, I know now where it has to be inserted, right? But there is no space, right? So I need to split this node L into L and L2, right? So how do I split that? So I take 2 star, then I put it 3 star, right? Now each node is having how many entries? I should have a 4 entries, right? So I am putting the 5 and 7. So now what I am doing here is, let me show you in diagram also and parallelly on the board, right? So what I am doing here is, I found the correct leaf, right? And then I find that it has to be inserted. So I am doing 2 and 3 one side and I am inserting a 5 here, right? And 5 star, then I am having 7 star. I have split this node, right? And then I can insert now 8 star, right? So this node got split up here. So this will appear here. Now what is happening? I need to adjust now the index entry for this, for the L2. So this became my L. Now this was my old L. Now this becomes my L and this becomes my L2. So I have split up this page into this. I am inserting a record 8, right? So I have split up now. So when I am split up this, now this will go, no? So let me remove this, right? Now what is happening? If I make it point it here, this record here in place of this, right? If I make it point it here, but now what happens? I have this node, no? So I need to adjust now in index entries also, right? So when I'm adjusting into index node, I find that there is no space here. I need to insert this 5 into this, right? So what I do is, now I split these index entries also. So let me put it little up here because I split that same node, no? So how did we split that? I had a record with 2 and 3, right? 2 star, 3 star, this was my leaf node. I had split that. So now one more node got added here and that was what? 5 star old, my 7 star was there, and now I am adding 8 star and there is a space for one record, right? So now what is happening? I need to make an entry for this, no? Right? For this node. Entry for each node beginning, there has to be entry into the index node. I cannot leave it like that, right? Minimum entry is how many? What is the order of my tree? My order of the B tree is 2, right? So minimum entries are maintained 2, that's why I pushed up here 2 and I inserted it here. But now if I point it here, what is the meaning? Less than 13 you will get, but greater than 13 you are getting here. But I need to have an entry for this. So but now when I want to make an entry for this L2, first entry I have to make it here. Now there is no space in the index. So what is required is, I should do the split the index node also. Fine. So when I am splitting, see it was 13 here, no? So how do I splitting here? I need to add 5, no? So what I will do is, see, I will show you here because it is better parallelly, because how I am doing, I am having, now I had a 4 entries. Let me put a very important point I am discussing. So 13, 17, 24, 30 were my index entries. Now I need to add a 5 into this index entries. But now it is already full. So I am splitting this into 13, 17, 24, 30. I can split it, right? But after splitting, what will happen? I will get the two spaces free. Suppose if I am not putting here 13 and 13, 17 here and 24 and 30, right? But I cannot have a 2 root nodes, no? So I should now make an entry for the root node. So what I am doing? I am taking a root node as the first entry which was here, because I am adding now 5 also, no? I need to add 5. So 5, 13, 2 nodes I am maintaining. So what I have done is, I will make here 5 and 13, right? So 5 entry has to be made for this node, right? So less than 5 are here, right? Greater than 5 are here, right? But less than 13 are here. So this pointer should come here now, right? Fine. Now what is happening? My greater than 13 are here, right? So my pointer is coming to here, greater than 13, right? because I changed the values now. My pointers are changing now. So now I create a one more node here, right? What are those entries? I am having the 24. I should have an initial entry less than 24. So I have a 24. Then I am having a 30. And now I make a root node with the 17. Right? Because I should have only one root node. So now it is how happening? Less than 17, I am saying go to this node. Because here I will get all the entries with less than 17. Greater than 17, go to this level 2, another index node. Right? So now what was required? There was a split required in the leaf node also, and there is a split required in the index node also. And as index node was full, we needed one more leaf node, the root node, to be pushed up. Right? So initially how I had only one root node with 4 entries. Right? But when I am inserting a record with 8 now, my tree changes. Right? So let me revise first step. I found the correct leaf where the 8 has to be inserted. Then I found there was no space for 8 record to insert the record with 8. So split up was done of that leaf into L and L2. Why 2 entries? Don't forget the order. So there has to be at any time in any insert and delete operation, the DBMS will maintain the minimum 2 entries in each node. Right? So with the split up is done with 2 and 3 here, and then 5 and 7 here, and then 8 was inserted into L2. But now there has to be an entry for new leaf node. So when I am doing an entry into the index node, we observed it was full. So again a split is required for the index node. But when I am splitting, they become 2 now. So I need to create a root node. So my entries, how did we adjust? We said 5, 13, then 24, 30, and then 17, which was middle, we pushed it up. Right? I hope it is clear. Right? How the insertion in the B+ tree takes. So now let us find out another example. This is the one which I have already put, right? The final tree. What is happening, see? Which I already put on the board. 5, 13, 24, 30. This is the final tree after inserting the 8. Right? So see now I am getting greater than 5. I will be pointed here. Greater than 13. I am getting the next node. So I hope it is clear. Example. How split up at the leaf node is required. How split up at the index node is also required here because index node was full. And with that, we need to insert a new root node. Right? Okay. So now you can say that, in earlier, there is another option called available is redistribution. But usually the redistribution does not, is not followed because many times if there are inserts and deletes, then it will become like a tedious work. All the entries to be changed, right? So my B tree is, suppose this was my initial B tree, no? So you could say that 8 can be inserted here and just redistribute the records. So we are discussing another alternative which is redistribution. But usually this is a possible option, but DBMS does not do this. Right? What you can say, push this 16 here, 14 here, you make it here 8 and just change this index because 8 is my first entry, no? So there has to be entry for 8 here. Right? So greater than, less than 8, I am having this side, greater than 8, I am having here. That is another possible. I hope you understood what we are saying. The 14, 16, we can push it here, 16 can be placed here, 14 can be placed here, and 8 would have been inserted here. That is another option, another alternative. And this is called as a redistribution of the records. But this redistribution will affect what? Many times, if inserts, deletes are there, this may not work. So DBMS does it. How? If there is no space at the correct leaf, then only it does split in that particular leaf. Right? So another alternative is redistribution, but which is mostly not used by the DBMS. Okay. So let us continue with the delete, because we avoid the redistributing the entries, right? So as the root was split, Now it leads to the increase in height. When the height of the tree will increase? If you are splitting the root itself. If you are not splitting the root at the second level, if you are splitting, then just entries at that level will increase, right? Okay. So now we see the delete data entry from the B+ tree. So again I am going theoretically, right? First, what we do, start at the root naturally, find the leaf L where entry belongs. Now we are deleting a record, no? So we have to find out a leaf node, right? Where that entry is there, because I am deleting a record with, suppose I want to delete a record with 19. Then I should find out first from the root. I should follow the path where the record is there with 19. Then remove the entry because I am just deleting. But what are the other effects? I should maintain the order of the tree, right? So just see whether leaf is now empty after deleting that record. Now in this case it will not be empty. Why? If I am deleting one record, because order of my B tree is 2, right? So I should have minimum 2 entries. So whenever I am finding, but if I remove another one more record, then it may happen. So if L is at least full, half full, done. Because what I say, if order is 2, I should have 2 to 4 entries. So half records are there means minimum 2 entries are there, then it's done. You need not worry, just delete the record. And always I have said you need not worry, I can do it means DBMS does that, right? So now what is next? If L has the less than D entries, that means D minus 1 entries, then what will happen? You need to redistribute it. You cannot keep a node less than D entries in B+ tree, because that order of the tree is always maintained. So if it is less than that, then redistribute happens. While redistributing, naturally again you take help of sibling, that is next node. So you borrow from the siblings and do the redistribution, right? Now if redistribution fails, then merge L and sibling. Suppose in sibling also there were less, then redistribution is not possible. Then what you do? You merge it and then both the nodes, L and sibling. So if merge occurred, then you must delete the entry from the parent. Because if you have already merged, if you have just done redistribution, entry need not be adjusted in index. But if you have merged the node L and its sibling, then you need to change the entry in the parent node also, right? So we will see with examples how possible things happen, right? So now I am deleting 19 and 20. Already I have inserted 8. So that same condition we are following. So I hope this tree is clear, whatever I have drawn it. Now I am deleting 19 first. So when I am deleting a 19, where is my record? It was here, right? So 19 and 20 both are considered here. So if I am deleting a 19 and 20, what is happening? I am having, deleting 19 was easy. First let us consider one case. Deleting a 19 was easy, so I will use the tree which is on the board. Fine. So deleting a 19 is easy because still my root has the entries, right? I have the entries 20 and 24, right? So I have 2 entries in the node. Fine. Now deleting the 20, what will happen? When I delete, now I need a redistribution. Why? Because I am having only one record here. Now what is redistribution required? I am having, what are the next records? Let me see the B+ tree. So let me go to my this tree, right here. So I deleted 19, I deleted 20, 19 I don't need any redistribution. When I am deleting 20, I need a redistribution because what are my records? 24, 27, 29, right? So I will go with, next records I have not written here, next row, right? So my next row was the 24, then I have 27, and then I have 29 star. Now when I am deleting this 19 was here, no? I deleted 19, record with 19, record with 20. So when I deleted 19, there was no problem because there were minimum M entries. My order is 2, right? So minimum D entries I had 2 entries. But when I am deleting 20, I need a redistribution. So how redistribution is done? The 22 is taken here into 24, right? So let me show you in the figure here itself. So my tree comes After deleting, here see, 22 and 24, right? So my 22 is here now, my 24 is here now, my 27 is here and 29 is here in this node, right? But now when I am doing redistribution, right, then entry has to be changed. So my entry got changed here, see, which was 24 in the index node, now it has to be 27 because the 24 got shifted from the sibling node to the previous node. So naturally my entry in the index node should change, right? So when this is needed, when you are redistributing using the sibling, because in this node there were no enough entries, the order of the tree, right? M entries were not there. What is my order? Is D. So my entries should be between D and 2D. So when you do a redistribution, what is required? In the up level, the index entry has to be changed. Fine. I hope it is clear. The index entry got changed there, right? So let us find out if I again continue with deleting 24, right? Say if I continue with another delete statement in DBMS, user has put it, and now he is deleting after this the 24, right? When he is deleting 24, what will happen? Again I need to merge these two nodes, the node L and its sibling, because now again entries are less. So when I am deleting this, right, the 27 and all, then I must merge this. When I am merging this, what happened? 22, 27 and 29. So this record has gone now. This node has gone. So to record with 22, record with 27 and record with 29, right? So now when I am doing it here, see now, the pointers, right, greater than 17, I am getting it here, greater 13, the less than 13, greater than 19, that is all is fine, right? So when I do it, then I must toss the index entry, that is pull down the index entry below. Why? Let us find out here. So when I am getting here greater than 17, right, but less than 30, then I should have a index node entry to be tossed up. Let us find out how we do that. Right? So what I am doing is, because I got a 22 there, greater than 17, but I may have, right? So when I am doing it at the end, what is happening is 22, 27, 29, greater than 30, fine, right? So I should pull down the index entry as we discussed now. Other things won't change here, right? So we are merging and we are changing the index entry for that. Now what was my index entry? Yeah, the point is here, right? What was my index entry? My index entry was like this, 17, then I had 5, 13 and 27 and 30, right? So now what has happened? I have removed the entries which are, like related to those 20, 24, all that. So now I need not go with 17, so I can pull down. That pull down means I am merging this node again, right? So I am merging the node 5, 13 and 27 and 30. So again the node becomes as, root becomes as 5, 13 and then 17 and 30, because I do not need this 27 to be maintained here, right? So I can pull it down because I deleted one node here. So the another option is I can take this 17 below, right? And then I am saying the less than 17, greater than 17 are here, my less than 17 are here, right? And my greater than 17 and 30 are here, right? And above 30 are here. So even I can merge the index entries, right? And then my root becomes again the one node, like it is reverse of addition. In addition, what happened? There was no space in the index, so we split up the index node and then we added the root node. Now what is happening? As my nodes are, decreasing, down leaf nodes, right? So I will adjust the index entries, but if I delete the whole node itself, right, then I may need to merge this, I can merge this so that I can have only one root node. Fine. I hope it is clear. Okay. So let us continue with the next part. Very important algorithms are in B plus tree are. One is the insert. Search algorithm is first. Second is insert. Third is delete algorithm. Right? So now let us find out the next topic. The last topic what we say here is the prefix key compression. So we discussed that. Now we know how B-trees are organized, how the things happen in B-trees, and B plus tree is the most widely used data structure, right? Used data structure for by the ADBMS, so that the access is fast, the indexing technique. Now we are discussing about if my index entries are the strings one. So if my index entries are, suppose because my key can be age, all these now examples we considered are my age values were like 5 star, 7 star are either age, or I can create an index on salary, or I can create an index on employee ID, right? So all these numeric fields I had. But suppose I have a index, the search key value as a string. String means if I am creating an index on employee name, right? If I am creating an employee name, then what will happen? I am saying this is a record with name Smith, this is a record with the name, Smack. Like that my entries will go, no? Again they are ordered. I started with S, or it can be like David, then I take an example which is with starting with D, right? So whatever names I am having in my database, all will be sorted even I am creating an index on employee name, right? So when I'm creating an index on employee name, right? So that time what happens? My key values, for example here, I'm considering my key values are Dynam Yogurt, then David Smith, then I am having the Devarkonda Murthy. So we can abbreviate. Now what happens, what point we are discussing is the key compression. My search key, if it is a string, then I need a key compression, right? So when I'm doing a key compression, I can do with prefix. What is prefix? We use the beginning words. Prefix is at the beginning, suffix is your end characters, right? Ending characters. Prefix is your starting characters. So for example, when I'm storing this name complete, the David Smith, right? So when I'm doing that on the name, then I need to store the complete name, David Smith, all the key values, and that will take a more space. And total number of entries, how many can be there in index, naturally depends on the search key value, right or no? So if I'm storing a string, I'm creating an index on name, and if I'm storing a key as my name, then that is going to take a definitely the more space. So I can store in a node, suppose with integers I could store 4 index entries, then with string it may happen that I'm able to store only 2 entries. Because every node is a page now. My root node is also a page on the hard disk. The second level nodes are also the pages. My leaf nodes also, each leaf node is a single page, right? Disk page. So now what happens? Based on the page size, my entries are naturally, how many entries I can put there is, I know, right? My page size is 4 KB, then my search key value, if it is age, then I know how many bytes it takes for the pointer, how many bytes, maximum how many entries I can have, right? So only we said order can be, between 100 to 200, means at the most in a page I can have 200 entries. But that is, that differs when I am having search key value integer and when I am having search key value numeric, the character one. So if my search key value is string, then the number of the, records I can address using the number of the nodes, all that the calculations will differ. So with that, what is suggested is you use the abbreviation for the keys if they are string, and you compress them. Compress is what? David I am using as a DAV, for example. So DAV indicates all the records starting with DAV, or your pointer will go like this. So instead of numeric, I am having here DAV, right? Then I am having DAV it is. Suppose I may have then DIN, M, right? Like that, because A and then I'm having I. So I'm saying all the records smaller than DAV are here and all the records greater than DAV but less than DIM are here. So I'm having here, you know, DAV, David, then I may have here the Dave, only Dave, DAV, right? So like that I may have entries here, right? But they are less than alphabetically when you convert into ASCII values, I am getting it there. So now what is the option told? What is we are discussing is, instead of storing the complete name like David, you know, David Smith. So you just compress it to DAV, right? And then you can use only prefix, that's why it is prefix key compression. So in the search key entries used using compressing, right? But when you are compressing, it is said that take care that left and right side all the tree is properly covered, fine. So whether you need to compress it to DAV or you need to compress it to DAVI based on the values which exist in the database, right? So I hope it is clear. Okay. So now the next topic which we are discussing is the bulk loading in the B+ tree. Right? So let me show you any key compression first, the example, I'll get it here. Right? So let me put it like, you know, B+ trees, the bulk loading example, and then we go with the bulk loading of B+ tree. So when we are creating a B+ tree, right, how can we fasten the process? So what we discussed is now how we can use the prefixes for the key, right? We compress the keys, search key, your key values, right? So that more entries can be in my index node. Now second point what we are discussing is how we can fasten the building the tree, right? So bulk loading B+ tree. So the tree, how fast it can be loaded means how it can be created fastly, fine. So let us find out bulk loading of a B+ tree. Suppose we are having a large collection of records and we want to create a B+ tree on some field, then doing so repeatedly for insertion records is very slow, right? So what is done? Bulk loading is done very efficiently. So what it does, naturally sort all the data entries, right? So all the data entries are sorted. So all the records with 3, 4, I hope it is visible. This is a record with 3, this is a record with 4, record with 6, 9. So all the records need to be sorted first, right? When you sort the records, right, the sorted pages of the data entries are now ready, but there is not yet entry into the B+ tree. So now you create a leaf node, the root node first, a new root page, right? And in new root page, naturally what will happen? I will have an entry of how much? See, now I had entries like 3, 4, 6, 9, right? So in the beginning, what will happen when I am having 3, 4? My first entry will be 6, because next leaf node I will get, no? So less than 6 and greater than 6. So these two will be covered when I am bulk loading next node, right? So what I am doing is, I am index entries for the leaf pages are always entered to the rightmost index. So let me put this. Once intermediate step is missed there. So let me put it here. 3 star, 4 star. This was my one page, right? Then I had, because I am assuming I can store only 2 entries for the demonstration for bulk load, right? 6 star and then 9 star. Then I am having a record with 10 and record with 11, right? Then I am having a record with 12 and record with 13. So when I am creating a root node, first node, naturally I have to make an entry for what? 6, because I will say less than 6 you point it here, greater than 6 you point it here. So now it is done. So when I am going, how many entries I can have here? Here also I will have 2 entries. Now it will be free. Only 1 entry is enough when I am loading the B plus tree. I am creating the B plus tree. Now why it is bulk loading? We are adjusting after sorting. How do we do it fast? Right? So when I am having here 10, no? So what I will do is naturally I will put it here 10, right? And I will say greater than 10 are here. Now when I am going with 12, my tree grows now here with, now it has to be split, right? So I create a node with 12 here, right? And I push this entry to the root. So less than 10, greater than 10, right? So usually the entries are pushed at the right hand side of the tree. Now when it is, I did it now this, less than 12, now what will happen? This pointer will change. Less than 10, then 6, greater than 6. Now less than 12, I will get a pointer here. And greater than 12, I will get a pointer here. Right? After 12, 13, I am doing 20 and 22. So my record with 20 and record with 22. Right? So what will happen? This 20, I am putting at the right node. So I am saying I will put it here. Why? Because right of the index node I put, then it will follow automatically, and then greater than 12 I got it here, right? First it will be placed here, and later when I am placing 23, next one, 20, 22, and then when I am going for 23 and 31, next record, 23 star and 31, then I have a space up. So this will be pushed up, right hand side entry, right? And then after 12 I will have a 23. Right? So I will get a 23 which is introduced here. A new entry for this, right? So I will get an entry for this. So like this, what happens is the order it and then you make an entry much faster than the insert operations. So you don't do for each insert. Concerted is once the records are inserted in the beginning in the application, then bulk loading of the data can be done into the, and the B plus tree can be easily built. Fine. So because your insert will take so many entries, so it is suggested that how DBMS carries out the bulk loading of B plus trees. So this is somewhere at the intermediate level. Again, if you observe, it is changing now. When I am going on adding, see now if you see the arrow this, now when you see the arrow already that is done, 3841, another page is done. So now again entries need to be adjusted because there has to be for each node, there has to be a starting of that and ending of that. So where are the entries less than that? So I hope it is clear, the bulk loading of the B plus tree, right? Now we summarize here. The option 1 is how do you build a B plus tree? Multiple inserts, but it will be slow, right? And then it is like, does not give option for sequential storage of the leaves. Second one option is bulk loading. That is what you do. You require a few IOs during build, right? Leaves will be stored sequentially, which are linked to each other so that the retrieval operations can be done very fast. Right? The ordered D concept is replaced by at least half full, naturally, physically, when it is put, physically we are saying. So to summarize, now I am completing the unit number 2, right? So to summarize the unit number 2, what we are saying, the tree structured indexes are ideal for the range searches. Also they are good for equality searches, right? The tree indexing structures are good for one for the range searches and second one for the equality searches, right? And then we saw 2 index structures, 3 index structures. One is ISM, second one is B plus tree. ISM we saw, it is a static structure, only leaf pages can be modified, overflow pages need to be added whenever required, right? The overflow chains naturally degrade the performance because first see the primary leaf pages, then see all the overflow pages, all that. But it is only suitable when you are using the when your data does not grow much, right? So in that applications we can use the ISM. B plus tree is a dynamic structure, right? Inserts, deletes, whatever we have done, my leave tree is always balanced. So if I'm maintaining a tree with height of 3 maximum with so many entries, so my height will be same and I can have 23 lakhs as you saw the entries, right? So it is always better than maintaining a sorted file, because in sorted file what happens, again you need to sort all the data, but here what happens, only that portion gets adjusted and I get in a search 1, 2, 3 disk IOs, whether I'm searching, whether I'm inserting, whether I'm deleting, right? Only those 2, 3 steps I require.